today. It's my pleasure to introduce Jose Bastidas. He's going to be telling us about generators for type B permutahedra via McMullen's polytope algebra.
Okay, thanks, Trevor, for the introduction. Can you hear me all well? Okay, so today I want to give you a nice type B analog of this result. And maybe we don't understand all the words here yet, but I will explain them. So the result says that every generalized permutahedron, so this is certain family of polytopes in RD, can be written uniquely as a signed Minkowski sum, and I'll explain what this is in a second, of the faces of the standard simplex. Okay, so and what I will do at the end today is give you a nice type B analog of this result, and I'll say what that B means. So let me start precisely with that. What are the two main objects here? Well, the nicely familiar permutahedron. This is the standard one. So this is the polytope, such that its vertices are all of the permutations of the points with coordinates 1 through D. So for example, in R3, we have a hexagon where the coordinates have all the possible combinations or permutations of coordinates 1, 2, and 3. And in the type B case that I'm going to denote with this extra B right here, we have this something similar. So all the permutations of the point 1 through D, but now we have signed permutations. So we are allowed to permute the coordinates, but we're also allowed to add negative signs whenever we want. And this is the result in R2, and this is the type B permutahedron, sorry, in R3. And the family of polytopes that we will consider are generalized type B permutahedra. So they are deformations of these polytopes. And there are many ways to define deformations, but for now, for today's talk, it's enough to think about polytopes such that the edges are parallel to the edges of the corresponding permutahedron. Okay, so in type B, for example, the cross polytope, or the octagon in this case, is a generalized permutahedron because all of its edges are parallel to some edge of the type B permutahedron. So this one right here is parallel to this, and so on. So this is a deformation of the type B permutahedron. And in this case, we have the type B permutahedron. I want to point out that the standard simplex, so the one that has vertices in the standard basis of RD, that's a type A generalized permutahedron. You can see this edge is parallel to this edge, and this edge to this edge, and so on. Okay, so this is our definition of generalized permutahedra for today. And what was the other weird word in the definition before? It was signed Minkowski sums. So what does this mean? Well, first, the Minkowski sum of two polytopes is defined like this. So it's a collection of points A plus B, where A is a point in the first polytope and B a point in the second polytope. And here we have an example of this foregone and its Minkowski sum with the standard simplex. So we can take this triangle and basically move it around this trapezoid, and what we get at the end, if we take all the possible sums, is this hexagon that we have right here. Okay, so that's the usual Minkowski sum. And I want to point out this is of course not unique. There are several ways to write this hexagon as the Minkowski sum of some polytopes, and here we have a different way to write it. So we can also write it as the Minkowski sum of these edges, right? I want to point out that in particular these are edges that are faces of the simplex. So this one right here is this face right here, and this one is just a dilation of this one. So these two right here means dilate that polytope by a factor of 2. And a signed Minkowski sum is what we get if we start moving things around in this equality. So what happens if I move this one right here? We're going to give some meaning to this difference. So sometimes this is called Minkowski difference. And a signed Minkowski sum is just some collections of sums and difference that actually makes sense, right? I can write, for example, an edge minus a triangle, but that doesn't represent any actual polytope because there is no polytope such that P plus the triangle gives me an edge. But some of them do make sense, like this one right here, and that's what we mean by signed Minkowski sum. And this is just an example of the theorem that I had before. This one right here is a generalized permutahedron, so all of its edges are parallel to the edges of the permutahedron. And here we have an expression of this polytope as a signed Minkowski sum of the simplex and its faces. And the point of the previous theorem was that, well, first, this expression exists, and the second one is that it is unique, okay? And we want to find something like this for type B generalized permutahedron. And for that, we're going to be working in this space, the space of virtual polytopes. So a virtual polytope is just a pair P comma Q, where both P and Q are polytopes. And I want you to think of this pair PQ as representing the Minkowski difference, P minus Q, okay? The point is that now we have pairs that maybe don't represent any polytope, right? Maybe I have here an edge and here a triangle, and that doesn't represent an actual polytope, but this is a virtual polytope. I want to think of this difference as it represents some virtual polytope. And then we have some relations, so I can have different pairs that represent the same difference, and that's basically what is represented here in this definition. But what is nice about this space is that it is actually a vector space, and the sum in this vector space is just the Minkowski sum. So we take Minkowski sum on each of the components of the tuple, and the real, so the way to multiply by scalars is, if the scalar is positive, we just dilate the polytopes. And if the scalar is negative, then I first need to multiply by -1. And what I do is just swap the order of the tuple. Basically, I'm reversing what I want you to think as P minus Q, and it becomes Q minus P, which is what you would expect if you're multiplying by -1. So this is just a formal definition. This is a vector space. But the nice thing about this vector space is that signed Minkowski sums that are sometimes complicated, right? It's hard to know if something actually represents a polytope or not. Here they just become linear combinations, and we don't worry too much about if they do represent a polytope or not. They're just formal pairs. So that's nice. It simplifies things a little bit. And let's see what happens in type B. So first, let's restrict ourselves to the case of, to this subspace where all the tuples are of this form. P and Q are both type B generalized permutahedron. We know what the dimension of this space is. So we know here we have this number. Let's not worry too much about this number, but the important thing is that we know how many elements I need to get a basis of this space, right? And that would be, in type A, we had the simplex and all of its faces. So we know how many of those there are, and those formed a basis of the corresponding space. Now we know how many do we need to get a basis of this space for type B permutahedron. So we know the number of polytopes that we're going to need. And for some reason that I'm going to skip for now, the nice analog of the simplex in type A, in type B would be the cross polytope. Okay, I'm going to skip the reason why this is the nice analog. But unfortunately, this doesn't work. If I take the cross polytope and I consider all of its faces, I don't get a basis of this space. Okay, and I get a space that is, I'm generating a space that is only of half the dimension that I want. And the reason why I only get half of the desired dimension is not too hard to see. For example, I can check that opposite faces, like this triangle right here and this blue triangle right here, if I look them from the right perspective, they're just generalized permutahedra. So like the standard simplex and its opposite. And all of those are generalized permutahedra of type A, the usual generalized permutahedra. So we already knew that this simplex and all of its faces generate all of them, right? So these faces right here generate all of the ones that are on the opposite side. So somehow I have redundant generators, and I'm not going to get the desired dimension. I'm only going to get something of roughly half the dimension. Okay, so this doesn't work. And then we have to look up for hints somewhere. And it turns out that, okay, there is this object that was in the title, but I'm not going to explain what it is, but there is this object that is the polytope algebra. First, the general one, it's infinite dimensional, but there is one that is smaller and restricted to the deformations of a fixed polytope, in our case, the type B permutahedron. And what we get is a finite dimensional graded algebra. And the first graded component of that algebra is, as a vector space, isomorphic to this space of virtual polytopes that I was discussing. Okay, so for today, I'm just going to focus on this first graded piece, but the story can be extended to all the full algebra. And the main result here is that there is, so this is part of an algebra, but we're going to give a different algebraic structure. We're going to consider this as a module over a different ring. Okay. This modular structure is described right here. So let me tell you in an easy example what this means. We're going to act on pairs of deformations, and I'm going to do the same procedure on each one of the elements on the pair. So let me just take one deformation of the type B permutahedron and tell you what the action is. Here I have Q, and I'm going to act with a phase of the, if you want, the normal fan of the type B permutahedron, or that's equivalent to say a phase of the Coxeter arrangement of type B. This is a hyperplane arrangement, and I can get, I see some cones in this arrangement, so like this two-dimensional cone or this one-dimensional cone. And these cones act on the deformations of the polytope. And the way that they act is I pick a phase, I pick a vector in the interior of the phase, and I look what's the phase of that deformation that is maximal in that direction. So in this case, I'm just considering, okay, what's the phase that is farthest away in this direction? And in this case, it's this segment right here. Or similarly, if I act with this phase G, I can take any vector in the interior of G, and I can see, okay, what's the phase of Q that is farthest away in this direction? And it turns out to be this vertex right here. Okay. And this turns out that this gives a modular structure. So I haven't explained what's the ring behind it, but it's generated by these phases. So let's leave it as a black box for now. But the important thing is that just purely algebraic stuff, we can get some decomposition of our module into smaller things. These are subspaces that they're not precisely submodules, but we have certain decomposition into subspaces. These subspaces are indexed by the flat of the arrangement. So we have that hyperplane arrangement, and a flat of that arrangement is just an arbitrary intersection of hyperplanes. So I can intersect no hyperplanes and get the full space. That's an example of a flat of the arrangement. And on the other end, I could intersect all of the hyperplanes. And for this particular arrangement, if I intersect all the hyperplanes, so these 4 hyperplanes here, what I get is the origin, just the origin. So that's another flat of this arrangement. And the main result here is that we computed the dimensions of these subspaces that we have right here, okay? And they are completely determined by certain combinatorial information that maybe I won't have a lot of time to explain what this is, but this is just, we're counting sign permutations with certain conditions over statistics, okay? So sign permutations act on RD by permuting and changing the signs of coordinates. So just like in this example right here. And this fix right here is just saying, okay, what's the collection of fixed points by that action? And I want that collection of points to be equal to the flat that I'm saying here. So in certain intersection of hyperplanes, I want that to be fixed by the action of this permutation. So that's the first condition. And this other condition is, okay, certain numerical invariant of the permutation that I'm going to skip for now. But now, how can we use this to get anything about generators for type B permutahedra? Well, remember that we have this decomposition into subspaces. The previous result tells us that the component indexed by that minimum flat, so the intersection of all hyperplanes, just the origin, has dimension 2 to the d minus 1. Okay, so this is counting sign permutations that only fix the origin and that have that invariant equal to 1. It's not hard to do. And the other key thing is that if we take any pair like this, so a polytope and a point, so this is representing the difference between these two, which is just the polytope itself. If we take something like this that is not full dimensional, then the projection of this pair to this space is 0. Okay, so that's going to imply that if I have any basis of this space of this form, because when I project it to this subspace, I'm still going to get a generating set. I needed to have at least 2 to the d minus 1 that are full dimension. Okay, and as a consequence, I cannot have just a single polytope and all of its faces and generate the whole space of deformations. That's not going to happen, like in type A. That cannot happen in type B. Okay, so now the question is, okay, I know that I need at least 2 to the d minus 1 full dimensional ones, but can I actually get them? Can I actually construct a family that attains this minimum, for example? And okay, we weren't that far away from the right answer before, so we can still consider the cross polytope. So maybe I should have said this before. The cross polytope is just the convex envelope of all of the basis vectors, the canonical basis vectors, and their opposites. So E1 and negative E1, E2 and negative E2, and so on. Here, E3 and negative E3. And what we're going to do now is slice this cross polytope with all of the coordinate hyperplanes. Okay, and if you count how many full dimensional polytopes you get, if you do that, well, you have one for each orthen. So you're going to have 2 to the d full dimensional polytopes. And we know that we might get along just fine with maybe half of them, right? If we pick them in the right fashion. And the final result that I want to share today is that, okay, there is an easy way to describe how to pick precisely half of them and some of their faces to get a basis for this space of generalized permutahedra. So maybe without going too much into the definitions right here, basically what we're doing is, okay, I'm going to take the full dimensional ones that live on the positive side of the first coordinate. And then for these lower dimensional ones, for example, I have these two that are just a translate of each other. I'm going to pick the one that it's positive on the second coordinate. And similarly with these two live on x2 equals 0. So I'm going to pick the one that it's on the positive side of x1, and so on. Yes, and I want to show you here, these are the family of generators that we obtain with this procedure in dimension 3. Okay, so now we have a very concrete way to do this. And I should point out, so this is how far I have reached in this project. But now that we have this family, there's a lot of things that are open for grabs. So now we can start wondering, okay, because every type B generalized permutahedron can be written uniquely as a Minkowski sum of these, let's find formulas for the volumes of those polytopes in terms of the coefficients that are arising from those sign Minkowski sums. So that's something that's still open, and that if anyone is interested can contact me if you want. Again, with that, I want to finish.
Thanks so much, Jose. Great talk. I'll invite everyone to unmute themselves and give Jose a round of applause. Does the audience have any questions for Jose?
Ayla put 2 questions in the chat.
Oh, I haven't seen.
I can read them for you. So her first question was, have you explored a type D analog for the theorem you're describing in type B?
I haven't yet. I think it might be possible. But so I didn't have a lot of time to explain what these invariants are. But there is one key property. So there is an analogous result for this in type A. So in type A, we already know generators, but still the polytope algebra, it's interesting to study the module structure that arises there. And there is an equivalent statement in type A. And what changes is this part, right? This part is the same. The permutations still act on RT. And if I pick a particular permutation and I see what's the collection of fixed points of the permutation, that's a flat of the Coxeter arrangement of type A, so the braid arrangement. That part stays the same. But this part, basically I had to, well, this is not new, I didn't invent this, but I had to pick the right statistic over the permutations that has a nice behavior with respect to the cycle decomposition, quote unquote, of the permutation. So in type A, what works is exceedances. So I should say, if you know where this comes from the H vector of the permutahedron. And usually you think of that in terms of the descents of permutations. But descents don't quite work because the property that we need is that the statistics is additive on the decomposition of cycles. So just as an example, if I have a permutation that looks like this, there is one, this is a type A statistic. There's one statistic that is called the number of exceedances of the permutation. And this is just the number of integers 1 through n that through the permutation go to something bigger. So in this case, an exceedance is 1 because it goes to 2, that's bigger, 2 because it goes to 3, 4 because it goes to 5, and that's it. Right? So the number of exceedances here is 3. And this statistic is additive, right? I could compute the number of exceedances here and the number of exceedances here and take the sum of those. And that's the key property that we need in the proof of this result. And it turns out that this statistic right here is additive in the corresponding notion. But I wouldn't know what the correct notion for a statistic would be in type D, sorry. So there are things to explore there. There must be someone that works, but I'm not sure what a statistic works yet.
I think you incidentally answered her second question, which was, she wanted to know philosophically why type B was the next type to explore.
I think, so I'm I'm interested. Yes, I think that type B, well, we understand, we have a lot of concrete combinatorial notions for all of the geometric things that arise from the type B Cox arrangement. And I think we know them pretty well in type B, but not in other types. So we know that, for example, flats in type A, there are just flats of the braid arrangement. They correspond to partitions. In type B, we have a right notion of signed partitions, or partitions of a signed set. But in other types, it's not so clear. So in that sense, in that setting, type B seems to be the right analog. And the other reason is that a lot of the polytopes that have been arising in different combinatorial aspects. So, for example, in a talk this morning about partial permutahedra, it seems that the polytopes that are arising there are type B generalized permutahedra. So finding a basis like this might be very useful for the people that are working with these polytopes. So I think that's why type B seems more interesting to me at the moment.
Awesome. Thanks so much, Jose.